What's up, guys? This time we're going to be getting into differentiation. So once again, like I did in the intro to calculus, no, sorry, limits and continuity. I'm not going to talk about differentiation right in the beginning. I'm going to just talk about before. I'm just going to set up a situation to then introduce why differentiation is relevant and important. So this first graph is what we're going to use later on. So let's focus on this graph. So this is just the most plain line you're ever going to see. Well, apart just from a straight line um, over the x-axis, over the y-axis. But this is just y equals x. It goes up by 1 each time you increase the x value. So remember, uh, whenever we want to find the line for the average rate of change for a line, our line is y equals x. Remember, average rate of change, average rate. That's big. Let me just go ahead and make that a little bit smaller. I'm gonna write a little bit. Average. Oh man. Average rate of change. Sorry, it looks bad, but let's roll with it. So remember, average rate of change. Let me just go ahead and draw the 2 points I'm going to find here. Let's say we're finding this. Let's just say that that's, I don't know, equal to 8. And we want to find this here. So since it's just a completely straight line, it has a constant rate of change, which means there's no problems as long as we find the average rate of change for one secant line, which we're defining right now. It's going to be the equation for the entire line. And let's just say this is for, let's say this top value is just 8 because it's just x and then that's 4. So remember, average rate of change is just y squared minus y1, which is the difference of y. Difference of y can be can be written as delta x. Delta x, remember, is just delta is just the change in. So this thing just says change in y. Bottom same exact thing, delta x. So this is our equation. So let's just go ahead and substitute in. So y squared. So I mean, not really y squared. I mean y2 is going to be 8 minus y1, 4 over x2, 8 minus 4, which is going to be 4 over 4, and down here it's just going to be equal to 1. That is our average rate of change, or slope. So that is what we have here. This is what we have here. Y equals x. There's no problems here. Since it's just since this entire line is just straight, it's completely fine. There's no change in the rate of change. But what if the line wasn't straight? This is where differentiation comes in. So let's say we have a line like this curve over here. Uh, so let's just try to find the average rate of change of this line. Let's pick out 2 points. I don't know. I'm just going to say it's a function, and I'm just going to try to be as general as possible, no specific numbers. So, oh, actually, let me just put some numbers. I'm just going to put random numbers, okay? This is not the function. It's just for an example. So let's just say this is uh, 8. Let's just say that's 6. Let's say this top number is 10. Let's say the bottom number is 4. Oh, sorry. So what we're doing, let me erase that. So what we're basically just doing is we're finding the average rate of change of the secant line here. So it's basically as if we're just putting a line here. Um, let's just do it. So that's 10 minus 4 over 8 minus 6, which is going to be equal to 6 over, what is that, 2? That average rate of change of that secant line we described as 3. But what if we change the secant line? What if maybe we turn this into 10, and if that value is, I don't know, 20, and we do the same thing, but this time the secant line is up here. Now you can see that average rate of change is not effective. Let's prove it. Um, 20, we're going to 4 minus, oh sorry, minus 4. Let me delete that just so we don't get confused. That's not a negative, it's just there. Okay, and then what is that? 10 minus 6. So that's 16 over 10 minus 6, which is 4. 4. So look at this. Average rate of change, they're different, but we can't have that. This is where differentiation comes in. Differentiation is basically just equal to derivatives. Derivatives. I'm going to delete the average rate of change work we did. So and let me I'll keep those tangent lines, but I'm just going to delete the x values and the y values. So what we can use differentiation for is to create derivatives. So let's say, and let's make this as general as possible. Let's just use another 2 points and we'll use a tangent line. So we're going to create that. I'll fix the line in a little. Okay, so let's pretend this line was just the exact same. Oh man. All right. One more thing to erase. All right. So we have those 2 points. So let's just label them first. So this first point, just x, and remember it's just a function of x. So this is just going to be the function of x. Okay. So what is so now we have to find x2 and y2. So what we want to do here is we want to make a general equation using the derivatives. So we're finding the derivative of that first x. There's different notations. Let me just write the most common ones down. Since this is a function, it's not a y, we can write it as this, d over dx of f of x. That is equivalent to f prime of x. That's what we can use. Those two. Those are the most common ones. If you have y, you can use dy over dx. You can also use y prime. But I'm gonna delete those last two. The most common ones are really f of x. I mean f prime of x, and then d over dx. Um, d over dx is just derivative. It's basically just saying derivative. So derivative of x. Those two are just the exact same thing. Let's just use derivative of f of x, the first notation. So we want to find the derivative of f of x. So what we're trying to do is basically find the derivative of this point. Oh man, sorry about that. Let me fix that. Okay, we want to find the derivative of this point right here of f of x. And so what we have to do is we have to find the equation of the line tangent to that point. So what we're basically just doing is we're finding the equation of the line that's tangent. So remember, tangent just means that it's touching that point. No, this is pretty difficult. No. All right, let's just roll with that. So this point that we had, it's covered up by the 2 secant lines we've made and the original graph line. The bottom line right here, this one right here, that's the tangent line. whenever we're finding a derivative, we're basically just finding the slope of the tangent line, and we can use a derivative to find the general like uh, derivative equation of a line. So what I mean is, let's just go ahead and find the average the slope of our original secant line. So it's x. We want to make this general. So the difference between the first point and the second point, it could be a specific point, but if we want to make it generalized, we want to make it the second point, we want to make it x plus some distance. It could be infinitely small, so it can just be literally x. Let's just say it's 2. It could be just 2, and then x2 can be 2.001. It could be 3. It could be 10. It could be infinitely large. We don't know. So that's why we're going to put delta x, which is change in x, whatever change in x is there. So that means that the value of the value of the function at x plus delta x has to be f x plus delta x. Sorry about it, looks pretty ugly, but that is going to be the function. So let's write that equation. Let's write it down. Um, so the derivative of f of x is going to be equal to x2, which is the function of f x plus minus f of x over x minus x plus the derivative of, change in x. So it's x minus x. So let me just go ahead and delete it and rewrite it. So these two x's cancel at the bottom. And the whole thing really just ends up being divided over change in x. So this is the equation we derived by finding it. And this is the most general equation we can create. Next video, I'm going to be talking about one of the several rules of derivatives, and those are very powerful rules, but you don't have to use the equation. You can just straight up look at it and find f prime. So this is just a generalization of of uh, the derivative, and it's actually not just that. I'm sorry, I forgot a vital part. It involves some limits. We want to find the slope of the tangent line, but we can't find the slope of the tangent line unless we're getting infinitely close to that point, because remember, the tangent line has that point in it. It touches it. So if we want to find the slope of the tangent line, we have to find x2, which has to be infinitely close. So let's just say, like, you see how we have like one point here? Let me make my pen another color. We have to have like another point infinitely close, like right there, and then to be getting closer and closer and closer to find that slope of the tangent line, which eventually you'll find by getting just as close as possible. And we can just find that by using the limit. So as delta x reaches 0, as the change in x from the original 0, x reaches 0, so as you get closer and closer to original 0, you'll find the limit. The limit. And so that ends up you end up finding the slope of the tangent line. This is the most general equation you can have. This can be used for like all equations. So remember that. And that's about it to you.